Let's work through a review for chapters 6 through 9. So our first question here says your company's average sales per quarter are $300,000. Population standard deviation is 25,000, and your manager comes to you with these questions. They want to know what's the probability that the sales will be more than $350,000 this quarter, and then what's the probability that we'll make less than $280,000 in sales this quarter? So the first step with a problem like this is figuring out what we know, right? We know that our mean is 300,000. So we'll type that out. And we know that our population standard deviation is 25,000. And then we'll be able just to reference those cells when we start using our different formulas. Right? So our first step here is for sales more than $350,000. We know our mean, we know our population standard deviation. We're going to need to know one other piece of our z-score formula, right? So our z-score formula is our x minus our mean all divided by our population standard deviation. Well, we know our mean and our population standard deviation. Our x is going to be this $350,000. We want to know where that's going to fall on our bell curve. So in order to find our z-score, we'll use that formula. We'll take our x of 350, subtract out our mean of 300,000, and then divide that by our population standard deviation. And we see that our z-score is 2. Now, that's just a piece of what we're trying to find here, right? We're trying to figure out what's the probability that our sales will be more than 350,000. So, once we have a z-score, we can find out probabilities using norm.s.dist, and that needs two different pieces to it. That needs a z-score, which we just found is 2, and then we type in true. And that gives us this number of 0.9772. So that's the probability that it will be less than $350,000 in sales. So for our purpose, we want to know the probability that it'll be more than 350. So what we need to do is we need to take 1 minus this 0.97 amount that we just found, and this will give us 0.0227. Right? So that means that there's just a little bit more than a 2% chance that we'll make more than $350,000 in this quarter. So our next part, we're to figure out sales less than 280,000. What's that probability? Well, we're going to need to use that z-score formula again. Right? So we have that z-score formula up above, our x minus our mean divided by our population standard deviation. Again, we still have our mean and our standard deviation given to us. Here, our x is going to be a little bit different. Instead of 350, we're now dealing with 280,000. So, we find our z-score by taking our x of 280, subtracting that by our mean of 300,000, and dividing it by our population standard deviation. That gives us a z-score of negative 0.8, which is just a piece of the puzzle, right? And then we need to find our probability by doing norm.s.dist, put in our z-score, and we type in true. And that comes back with 0.2118. Now, in part A, up here, we had to subtract this 0.97 from 1, right, to find our true probability. Because we wanted to know the probability that it would be more than 350. Well, Here, when we want to know the probability that it'll be less than 280, that's what this 0.21 represents. That's the area to the left of negative 0.8 in your bell curve, which means that that's the probability that it will be less than $280,000 in sales this quarter. Now, our second question here, we're told the average price of a new car is $33,000. The population standard deviation is $3,500. 500 people bought new cars in Phoenix last month. What is the probability that a random sample of 45 car buyers in Phoenix last month spent within $1,000 of the average price? So again, just like what we did in the first problem, we're going to figure out what we're told, right? We're told that the average price of a new car is $33,000. So that's our mean. Population standard deviation was 3,500. And then we need to think about our n. So a lowercase n is our sample size. If we were told that 500 people bought new cars in Phoenix last month, that would be the population. That would be the total amount of people that bought cars. What we're thinking is we just want to pick 45 of those people at random, right? So our sample size is this 45. Now, we're trying to figure out probabilities here, right? What's the probability that we're within $1,000 of the average price? In order to do that when we're doing the sampling distribution like this, we're going to need to know our standard error. So our standard error is going to be our standard deviation, this 3,500, divided by the square root of our sample size, right? So we select the cell that has our population standard deviation. We divide that by the square root of this 45, and we find our standard error to be this 521. Now we can use that to help us figure out these probabilities that we need. Because our z-score formula now is going to be x bar minus your mean, all divided by your standard error. So it's a little bit different when we're working on a sampling distribution, but it's the same ideas as we're going through this. So we want to know the probability that we're within $1,000 of the average price. That means $1,000 on either side, right? So we're going to have two different X amounts. We're going to have an X amount of 32,000, and then we're going to have an X amount of 34,000, right? Plus and minus 1,000 from this mean of 33,000. We're going to want to figure out our z-scores for each of these. So we said that our z-scores will be these X bar amounts minus our means divided by our standard error. So we find that for the 32,000, and then we do the same thing over here for the 34,000. So our X bar minus our mean, all divided by our standard error. Now, since they are equal distances away from your mean, you'll notice that the numbers are the same. It's just one's positive, one's negative, right? Because they're each 1.92 standard errors away from our mean. So we have our two z-scores here. And we want to know the probability that it'll be somewhere between. So what we'll do is we need to find these probabilities just like what we did in our first question. So norm.s.dist, we select our z-score, and we see that the probability of less than 32,000 is this 0.02. Then we need to know the probability that it will be less than 34,000. So norm.s.dist, we select our z-score and we type true, and we find that to be 97%. Now, to know the probability that it will be somewhere between 32,000 and 34,000, we then just subtract our two probabilities. So we take the 0.97, subtract the 0.02, and we can see that the probability that a random sample of 45 car buyers spending within $1,000 of our average price, that probability is 0.94, or a 94% chance. Now, question number 3 gets into confidence intervals. So we're told that a sample of 55 days showed the average temperature to be 85 degrees. The population standard deviation is 4 degrees. We need to provide a 95% confidence interval for the population mean temperature. And then we're going to show what happens when we lower our confidence level, right? We're then providing a 70% confidence interval for the population mean temperature. So once again, we need to think about what we're told. So we're told our n, our sample size, is 55. Our x bar, the sample mean, is going to be 85. Our population standard deviation is 4. And now that's going to be the same for both of our intervals, right? So we can put that over here as well. Now, just focusing on part 1 here, we're looking to provide a 95% confidence interval. So we need to think about what alpha is. Alpha is going to be 1 minus your confidence level. Our confidence level is 95%. So 1 minus 0.95 gives us an alpha of 0.05. Now, when working on a problem like this, we don't just want alpha. We're going to want alpha divided by 2. So we can take the 0.05, divide it by 2, and we see that our alpha divided by 2 is 0.025. So what is a confidence interval, right? Our confidence interval is going to be our x bar plus and minus our margin of error. So if we think about what our margin of error is going to be, that's going to be your z-score of alpha divided by 2 multiplied by your standard error. So there's a couple different pieces that we need to find here, right? We need to find our z-score of alpha divided by 2, and we need to find our standard error. Let's first work on our standard error. We said earlier that your standard error was your population standard deviation divided by the square root of n. So, population standard deviation divided by the square root of our n, and we see that our standard error is going to be this 0.539. Now we can find the z-score for alpha divided by 2. And how are we going to do that? So we know our alpha divided by 2 up here. This is that 0.025. What we can then do is do norm.s.inv, INV, and then that's just asking for a probability. That's where we put in our alpha divided by 2 amount. And that gives us back this z-score of negative 1.96. So it would probably be easiest to work on our confidence intervals using positive z-scores. So I would always recommend multiplying that by a negative 1. And then we're just going to reference this positive 1.96 in our calculations. So taking a look back at our confidence interval formula here, it was our x bar plus and minus our margin of error. And we said that our margin of error was our z-score for alpha divided by 2 times our standard error. Well, now we have our z-score, and now we have our standard error. Right, so now we can work on our margin of error, which is just going to be that z-score times our standard error. And we get this 1.057. So that's going to be our margin of error here. So when we figure out our confidence interval, we'll have a lower limit and an upper limit. The lower limit, all we need to do is we take our x bar and we subtract our margin of error. And our upper limit, we take our x bar and we add our margin of error. So we now have our amounts here, right? The lower limit's this 83.9, the upper limit's 86.057. What does that mean? So that means that based off of this sample that we took, we can be 95% confident that the population mean temperature is somewhere between 83.9 and 86.05. Right? We can be 95% confident that that's what our population mean would be. So now let's take a look here at part 2 and figure out how this changes when our confidence level changes. Right? In part 1, our confidence level was 95%. Here in part 2, it's only 70%. So our n, our x bar, and our population standard deviation, all of those were the same. Our alpha is where this all changes. Right? So our alpha was 1 minus our confidence level. So here in part 2, 1 minus 70% gives us 0.3. Right? So 0.3 will be our alpha. The next piece that we did was finding alpha divided by 2. So we take our 0.3, we divide it by 2, and we get this 0.15. So that's the setup of every single confidence interval problem, right? Is writing out what you know, finding your alpha, and your alpha divided by 2. Then we can go to work on actually filling out the pieces that we need to know our margin of error and to construct our confidence interval. So we needed our standard error. Our standard error was our population standard deviation divided by the square root of our n. And you'll notice it's the same amount in each. Because what changed between part 1 and part 2 of this problem was our confidence interval, or our confidence level. Our population standard deviation stayed at 4. Our sample size stayed at 55. So our standard error wasn't going to change here between these two parts. What's going to change is our z-score. So we need our z-score of alpha divided by 2. And we found that by taking norm.s.inv. It's asking for a probability. So we put our alpha divided by 2 in there, and it gives us back this z-score of negative 1.03. And as we said earlier, it's going to be easier to work with the positive version of this z-score. So we can just multiply it by -1. And so now that we have our z-score and our standard error, we can find our margin of error. We take a look over at the left again. Our margin of error is that z-score that we just found times our standard error. So we take the 1.03 times our standard error, and you'll notice your margin of error is now just 0.559. Right? So as your confidence decreased, your margin of error decreased. So we now need to find the lower limit and the upper limit on this confidence interval. So we take our x bar minus our margin of error to find our lower, and to find the upper, we take the x bar and we add in our margin of error. So as your confidence level increases, our confidence interval is going to have to be wider. Right? Now, we're talking about temperatures here, right? So the best way to think about this is that I can be 100% sure that the temperature outside is somewhere between 0 and 500 degrees. But if you want me to narrow that down a little bit, my confidence will have to go down, right? I'm only 60% confident that it's somewhere between 80 and 82 degrees outside. So you'll notice that with the higher confidence level, you're going to have a wider interval. With a lower confidence level, you're going to have a smaller margin of error and a more narrow interval. Now, if we take a look at number 4, number 4 starts talking about these hypothesis testing that we learned about, right? So this problem says a production line operation is designed to fill cartons with laundry detergent to a mean weight of 32 ounces. A sample of 100 cartons is selected, and the average weight of the sample was 31.5 ounces. The population standard deviation is 3 ounces. Determine if the line needs to be shut down and readjusted using 0.05 as the level of significance. Once again, before we work through all of these different steps, right, we need to first figure out what are we told. Our mean is this 32 ounces. Our x bar, that's going to be the sample mean, right? So from that sample that we took, the mean was 31.5. Our n, that's the sample size, that was our 100. Our population standard deviation, we were told that that was 3. And then our alpha. Our alpha is either 1 minus our confidence level, like we just worked on in confidence intervals, or it's the level of significance, right? That's what alpha is. So we were told that our level of significance here was 0.05. So once we have that, we can then work on all of these different steps to this hypothesis test. So the first thing that we need to do is figuring out our null and our alternative hypothesis. So we know that we're going to be dealing with means, and we know that we're going to be dealing with our 32s because that was our population mean. The tough part here is figuring out the signs, right? Is it greater than, less than? Is it equal to, not equal to? So we need to think about this one here. And we are a production line. When would we shut down and readjust? Would we shut down and readjust just if we are overfilling? just if we are underfilling or whether we are overfilling and underfilling. So in this case, we would need to shut down and readjust our production line if we put too much laundry detergent or not enough laundry detergent in these cartons. And since we would reject on either side, that tells us that it is a two-tailed test. So we are going to have our mean equals 32 and our mean does not equal 32. Because both ends of that spectrum would be unacceptable for us. Now, step 2 was just to set a value for the level of significance. We already did that. Our alpha was 0.05. Now, we can find our critical value. So the critical value here is going to be a z-score. And it's going to be a z-score based off of your alpha. And we have to be careful here. If this was a one-tailed test, so if these signs up here in our hypothesis, if they were less than and greater than, that would tell us it's a one-tailed test. But here, since it's equal and not equal, it's a two-tail, which means that this alpha of 0.05 has to be split up between each of the tails. So we're going to want to find alpha divided by 2 whenever we're doing a two-tailed test. And we find that to be this 0.05. And we need that because our critical value here, this critical z-score, is going to be the z-score using this alpha divided by 2. So we'll do norm.s.inv. Once again, that one just looks for the probability, and it will give us back a z-score. And so it's going to be negative 1.96 again. Now, we said it's two tails, right? So that's going to be the one tail. The other tail is the positive version of that z-score. So we have two different critical values. We have our negative 1.96 and we have our positive 1.96. So those will come back into play later on in this hypothesis test. Next up, we need to calculate the test statistic and the p-value. So our test statistic is a z-score. And this z-score is going to be using the information that we were given up in the top of our problem. Right? We're told our mean, our x-bar, our n, and our population standard deviation. We're going to need all of those to find this test statistic. If we think about the formula for our z-score, that's going to be our x-bar minus our mean, all divided by our standard error. So, once again, we're going to need to find our standard error. Once we find that, then we can just plug in our other values and we can get this test statistic. Our standard error is our population standard deviation divided by the square root of n. That gives us a standard error of 0.3. Now, our test statistic, we can take our sample mean, our x-bar, subtract that from our population mean, right? And we're going to want parentheses around those. And then we divide that by the standard error that we just found. And that gives us a test statistic of negative 1.67. So that's part of this step, right? We calculated the test statistic. But then we need the p-value. And our p-value here, all that is the probability, right? Just like what we did back in the first couple questions. We just need to find the probability. So we take norm.s.dist, and it's going to be asking for a z-score. So we put in our test statistic, and we put true. And that comes back with 0.0478. Now, if this was a one-tailed test, that p-value would be okay. However, it's a two-tailed test. So what we are going to need to do is we need to multiply this by 2. Because what that's saying is that we will have 0.04 on either side. So the total p-value is this 0.096. That's going to be the total p-value here for this problem. Step 5 is comparing the test statistic to the critical value or the p-value to alpha. Right? We have two different approaches that we could take here. Let's start with the test statistic to the critical value. So our critical value starts what we call the rejection zone. So if we draw a bell curve here, and we have our critical values, and both of these are at 1.96 and negative 1.96. Our test statistic would come in at 1.67. So they are in the middle between our two critical values. These tails over here, to the right and to the left of our critical z-scores, those are our rejection zones. Since our test statistic does not fall within that rejection zone, that would tell us do not reject our null. So that's what we're doing when we're comparing our test statistic to our critical value, is we're seeing where it would fall on this bell curve. Now, the other approach here, the p-value approach, when we compare the p-value to alpha, we have this rule that we can follow, where if our p-value is less than or equal to alpha, then we would reject our null hypothesis. Well, in this case, our p-value is this 0.095, and our alpha is 0.05. So since our p-value is greater than our alpha, we once again say that we do not need to reject our null hypothesis. And no matter which method you use, it's going to come up with the same conclusion. So whether you are comparing your test statistic to the critical value or you're comparing the p-value to alpha, you should get the same final answer. So what's our conclusion, right? We said do not reject the null hypothesis. However, let's say you're doing this out in the real world, right? And your boss comes to you and they're like, okay, you just did all this work. What's your recommendation? And you tell them, don't reject the null. They're not going to know what you're talking about, right? You need to be able to put that into real terms. So our null hypothesis here was that our mean equaled 32. So if we're saying don't reject that, we're saying that we don't have enough evidence to say that this is wrong. There's not enough evidence out there to show us that it doesn't equal 32. So by not rejecting the null, we do not have to shut down and readjust the production line. So being able to figure this part out, your conclusion is incredibly important when working through a hypothesis test, because you're going to need to put it into real terms, right? So not only do we say do not reject the null, but we also want to say what that means. So our last question here is another hypothesis test. It's going to be slightly different though than what we just worked on in question number 4. So this one says that the Wall Street Journal reported that bachelor's degree recipients with majors in business received average starting salaries of $53,900 in 2018. The population standard deviation is $5,200. The results for a sample of 100 business majors receiving a bachelor's degree in 2020 showed a mean starting salary of $55,144. Determine whether the mean starting salary for business majors increased using a 0.10 level of significance. So once again, just like we've done in every other problem, we want to write out everything that we're told. So we're going to start here with our mean, right? Our population mean. So our population mean is this 53,900. Our X bar is the sample mean, right? This is when we look at the sample of 100 business majors. What was the average starting salary for them? That was the $55,144. Our N, that's just our sample size of 100. Our population standard deviation, we were told that was 5,200. And our alpha, that's our level of significance, and that's 0.1. So we've taken this whole paragraph and we've put it into just the pieces that we've been told. Now, step 1 is figuring out our null and our alternative hypothesis. So we fill in the parts that we definitely know. We put our mean and the 53,900. We need to figure out the signs. So this is when we look at that last sentence of that paragraph above. And it says, determine whether the mean starting salary for business majors increased. So your null hypothesis here is going to be whatever the test wants to show. So in this case, it wants to show whether it's increased over the past couple years, right? So we want to know, has it gotten bigger? So our alternative is going to be our mean is greater than 53,900. So what about our null? Our null is just going to be the opposite. Now, the opposite of greater than is not just less than. It's less than or equal to. So make sure that your null hypothesis always has the equality in it. Your null is always going to be the one that's less than or equal to, greater than or equal to, or like we saw in the last problem, just equal to. The alternative is only going to be greater than, less than, or not equal to. You'll never have the equality here in your alternative hypothesis. Now, step 2 is figuring out the level of significance. We already did that. That's just our alpha of 0.0 or 0.1. Now, in the last problem, we needed to find alpha divided by 2, right? Because it was a two-tailed test. In this problem, we can think, is it a two-tail or one-tail? So we take a look at our signs. And our signs have less than and greater than, right? So that tells us it's just a one right-tailed test. So we don't need to worry about dividing alpha by 2 here. Now, if you have just a one-tailed test, the next step is figuring out if it's a right tail or a left tail. The easiest way to do that is by taking a look at this sign right here, the sign in your alternative hypothesis. That arrow is pointing to the right. So it's a right-tailed test. That's going to be the easiest way to figure that one out. So if your alternative hypothesis has a greater than sign, the arrow points to the right, and so that's telling us it's a right-tailed test. So we'll keep that in mind because that is going to come into play here when we're talking about our test statistic and p-value in step 4. So now our critical value, right? This was just a z-score. And if we remember, we did norm.s.inv, and we just put in our alpha. And that comes back with this negative 1.28. Now, it's a right-tailed test. So that means that your critical value here, we're going to want to show it over on the right side of our bell curve. So this needs to be a positive value. So we'll just multiply this by negative 1, and this will be our critical z-score that we'll use in step 5. Now, our test statistic and our p-value. Again, our z-score formula is our x bar minus our mean divided by our standard error. We need to find our standard error here. So that's going to be our population standard deviation divided by the square root of our n. So that gives us our standard error of 520. And now we can find our test statistic. Our test statistic is just our x bar minus our population mean divided by the standard error that we just found. And we have this test statistic of 2.39. So that's part 1 of this step, right? Calculating the test statistic. The next part is finding your p-value. And we said the p-value was just the probability, right? So we took norm.s.dist, D-I-S-T, and we need our z-score, and we need true, and we get this value of 0.99. Remember, that's the value to the left. That's the probability that it will be less than that test statistic. However, this is a right-tailed test. So we are going to want to know the area to the right of this test statistic z-score. So we will take 1 minus this 0.99, and we now have this 0.008, and that is our p-value. Now step 5 was comparing our test statistic to our critical value. So we can once again draw out a bell curve. And it's a right-tailed test, so everything that we're talking about is going to be over here on this right side of this bell curve. Our test or our critical value was this 1.28, right? So we can come in here and we can put 1.28 as this critical value here. Our test statistic, however, this 2.39, that's going to fall even further over on this right side. And we said that anything that fell in this tail, anything to the right of our critical value here, because it's a right-tailed test, we said that any of those, we would then need to reject the null. So when comparing your test statistic to your critical value here, you saw that your test statistic fell within the rejection zone created by your critical value. Now we can compare our p-value to our alpha. And we had that rule where if the p-value was less than or equal to alpha, we would reject, right? So our p-value is this 0.008. Our alpha was 0.1. So we see that our p-value is less than or equal to alpha, which then means we need to reject the null. And you'll notice once again, we came up with the same conclusion no matter which approach we took. So now our conclusion here in step 6, right? So that's just rejecting the null hypothesis. But once again, we need to explain what that means. So our null hypothesis here was that the mean would be less than or equal to 53,900. Meaning the mean starting salary of business majors would have stayed the same or decreased. We're saying that we have enough evidence to show that this null hypothesis here is wrong. And instead, we're going to go with this alternative. So what we are saying here when we're rejecting the null is that the mean starting salaries of business majors have increased over the past few years.